Good morning, everyone, or good afternoon if you're located in Europe. I'd like to welcome you to our latest webinar in the series Scientists Empowering Scientists. Today we will talk about dynamic clamp with voltage-gated sodium channels, tips and tricks with two software programs, EgoPro and SADA-Patch. My name is Jan Dolzer. I'm the Director of Marketing at SADA Instrument. The agenda today, we will have a few short introductory remarks. Then Chris Herrick from Wavemetrics, a division of SADA Instrument, will talk about importing data into EgoPro version 9. The next speaker is Sam Brown from the Miami University in Oxford, Ohio, who will talk about using dynamic clamp to explore sodium channels in Purkinje neurons. And then Telly Gaetzatos will talk about tips and tricks with SADA-Patch, data acquisition management and analysis software. And then at the end, we will have a combined question and answer session. We hope that you hear me. If you don't, audio is transmitted over the internet connection, so you may want to turn up the volume on your computer. If you don't have speakers, you can also dial in by phone, and dial-in numbers for the United States and a whole list of other countries are available in the GoToWebinar control panel. If you have questions, you can also use their control panel. Please use the questions section. Please mention which speaker your question is directed to. Sometimes that's easy to guess, but we don't want to have to guess. And if the chat window is available, I think they disabled that for attendees now. But please don't use the chat window, use the questions panel. Makes it easier to manage. And all questions will be addressed either during the Q&A session at the end of the webinar, or if we don't get to it, we'll respond to it by email. Documentation, as usual, a video of the entire webinar and individual talks also will be available on our YouTube channel, probably within the next 4 weeks. If you've registered for this webinar, you will receive an email notification when the video is available. And ta-da! SADA Instrument is celebrating its 50th anniversary this year. 50 years ago, the company was founded, and since then we have released a large number of products, some of which may be familiar to some of you. I only want to quickly highlight our oldest product, still in production, the BB10 micropipette beveler, the first laser puller, the P2000. In 2016, we started releasing amplifier systems with the IPA, the Integrated Patch Amplifier, and SADA-Patch software that Telly will speak about today. And in 50 years, only a few highlights. The founder is Dale Fleming, who today, well into his 80s, is still in the office pretty much every day. SADA is privately owned, as many people don't seem to know. We're around 70, 75 employees, give or take. And our goal is releasing at least one new product every year. And another goal is excellence in tech support. What that means is the communication shall be phone tree free. If you call in, it usually takes one connection until you talk to somebody who is an expert in their field, either has scientific and or engineering background, and usually understands quite a bit about the science that you do. My last slide, just highlighting in the context of patch clamp. Most of you in the audience will probably be interested in patch clamp. This is a slice patch clamp rig, and you can get all components in that rig from us. We either make or distribute them, micromanipulators, products for micropipette fabrication. One of our pullers is in almost every electrophysiology lab. Mounting solutions, entry stands, platform stages, microscopes, perfusion systems, glass capillaries, the software, SADA-Patch software that Telly will be talking about, imaging products, equipment racks, amplifier systems, and air tables and Faraday cages. With that, let me introduce today's speakers. Chris Herrick received her bachelor in math and computer science in 2001 at the University of Oregon, then spent some time in Beaverton with integrated measurement systems and a lot of time with Qualcomm in San Diego, where she's still located today. In 23, she joined Move Medical San Diego, and then earlier this year, she joined Wavemetrics, division of SADA Instrument, where she's a senior staff software engineer. Sam Brown got his bachelor in biology, I assume, at the Miami University in Oxford, Ohio, and since 2020 is a graduate student there and studies the intrinsic excitability of several Purkinje neurons with electrophysiology, and that's what he's going to be talking about today. Telly got his bachelor in computer science at the Queen's College in 1987, joined Instrutech in various functions, finally as a general manager. And when Instrutech was acquired by Hecker Instruments in 2007, Telly became the general manager. In 2015, Hecker Instruments was sold, and Telly joined Sutter Instrument. And neglected to mention, Telly and I met during my time at Hecker Electronic, the parent company of Hecker Instruments. And since 2015, I have the honor to call Telly my colleague at Sutter Instrument, where he's today the product manager for the patch clamp systems. And with that, let me switch. Chris, you're the presenter.
Hi, my name is Chris Herrick, and I am an Igor Pro software engineer at Wavemetrics. Igor Pro is the root software that Sutter Patch is based on. Today, I'm going to talk to you about how to import data into Igor Pro. So I think that's a really important piece of the puzzle when working with Igor. And there's lots of different ways to import data, and I want to just walk you through some of the most common ones. This is Igor Pro that I have up right now. Here is the command window where you can type in commands. I'll just make a quick wave. We'll just name it W, and we'll put some real basic data in it. And if we display that as a graph, then you can see in the window browser, my available graphs and tables will be shown here. And here is the data browser that shows all of the waves that I have created. An experiment is the word for a collection of Igor objects. And these objects are stored in an experiment file that has a PXP file ending. It's very common for your data to already exist in another Igor experiment. And a lot of people don't know it, but it really is dirt simple to copy data waves from one experiment to another. So that's where I'm going to start. I'm just going to close this real quick. So in the data browser, there's these 5 buttons to the left-hand side, and the middle one is Browse Experiment. So if I click on that, I'm going to pick one of the experiment files that ships with Igor, the multi-peak fit demo. We just open that up, and you can see in the data browser the waves that are in the multi-peak fit demo experiment are shown here, and we can browse them and get a preview here in this bottom window of what the data looks like. I want these my X data and my Y data waves. I'm going to use the Shift key to highlight both of them, to select them both. And all I have to do is drag and drop them into my root data folder. And here they are in my experiment. You can also use the Command key to highlight more elements, to select other. You can even select entire folders, even everything in the whole. You can just pull over everything in the whole experiment if you wish. And you can have multiple of these open. You'd select between them here. And when you're done browsing and have all of the data that you want from that experiment into your new experiment, you just hit Done Browsing. So now let's look at these waves in a graph. So we just do display my Y data versus my X data. These wave names have spaces in them, so I've used single quotes to be able to use them on the command line. And here we are. Looks pretty good. And that was very, very simple. Another really easy way to pull in data is to import from an Excel spreadsheet. So I have an Excel sheet here, and these are actually the same waves. They're just copies of the same waves that I pulled in from the example experiment in the last step. I have a time series and a data series listed here. Excel doesn't like you to import or do anything with the file in the file system until you have closed the Excel spreadsheet. So I'm just going to close that here and then go back to Igor, and I'm going to import that spreadsheet. So I just go to Data, Load Waves, Load Excel File. I'm just going to hit File, and here's my simple data.excel spreadsheet. We're going to open that, and all of these defaults are fine. There's a wave names in the worksheet on row 1, double precision waves. If the wave name already existed, I'm going to overwrite. I'm going to get rid of the blanks at end of any columns. And here is the command that's going to be generated and run when I hit do it. So here we go. Here's my table. We can scroll through and see that the data came in nicely. And here are the new waves, X time and Y data. Let's graph that again. So this is going to be Y data versus X time. I didn't need quotes that time because these names didn't have any spaces or funny characters in them. And you can see that the data is exactly the same and the graphs look the same. So that worked great. One thing I also wanted to point out is all of the actions that I'm doing through the GUI, they have equivalent commands that you can either use on the command line directly or in an Igor procedure script. And most of the time when you run something through the GUI, it's going to print out, it's going to display in your history here in the command window, the command that it ran. And that's really, really helpful because especially for complicated commands such as load wave, it's a great way to get your command working, and then you have the command in your history, and then you can use that later in an experiment that you want to automate in some way. So we've pulled in the Excel file, we've shown how to do that. I'll just go over that again. It's data load waves. And here are all the different kinds of waves we can load. The next one we're going to do is, I'm going to show how to do a custom data format. So in this data file, I have one column that's dates and one column that's data. On the date column, you can see that this is going to be month, day, and year without any separators. Often we'll find that dates in particular can be in very interesting formats. Sometimes you're not completely in control of how the file format comes to you, how your data comes to you, and you have to just work with it as it is. Igor tries really hard to be able to help you parse whatever data has come to you as is without you making a lot of edits to your files beforehand. And one way that we do that is through custom formatting. So if you need special custom formatting for your data, you'll want to save the data file in a CSV. In this particular instance, I had this in a spreadsheet and I just saved it as a CSV file instead of an Excel file. And Excel made this for me automatically using a comma as the separator, as the delimiter of the data. So to import custom dates, what we're going to do is, again, we're going to go to Data, Load Waves. We're going to go to the Load Waves, this first one. And this is the full dialog for all types of waves. This data here does have names, so I'm going to say read wave names. I'm also going to have it make a table because when I load waves, I like to see the table right when it's imported, just to show what it's imported, what the data looks like, to make sure everything imported as I expected. And I'm going to keep double precision checked, and I'm going to go to this tweaks button. So here we want to focus on the date format option. We're going to choose other, and that brings up another dialog. Under common format, there's a lot of different options here. I want to highlight a couple things. If you, for example, have any of these options that say either abbreviated or full, that's going to include the names of the months or maybe day of the week, Monday, Tuesday, Wednesday, but it might also be in a different language. So you can select the language here. That's not relevant to this data particularly, but I just wanted to highlight that availability for you. We have month, day, year with no separators. So that's one of the common formats that's automatically there for us. And we can tell here in the sample section that this is what it's going to look like. Today's date is always one of the options to see. So it's 12/10/2024, and that's great. If we did, for example, if this was different in some way where we wanted to use a custom format, we can do that as well. We can have the year be 4-digit or 2-digit. We can have a numeric month with a leading 0. We can have abbreviated alphabetic month. So that would be DEC, for example. So we have lots of options. No leading 0 is also an option. And we can put them in different orders, and we can put in our own interesting date formats, whatever it may be, we have those options. But we're going to use month, day, year for this. There, that's good. And then we'll select the file. This is our custom date CSV file. We'll open that, and here's the command that's going to be generated, and we'll do it. Now, after you've done any custom tweaking, you'll see this preview of the data that's going to be pulled in. It named X date. That's good. The column format is number here, and we want to show it that this one's a date. So we're going to hit that, and this is the name of the Y data 2 column. That's just a number, double precision. That looks great to me, and we'll hit load. Now we can see the table of data that pulled in, and we can see that it is definitely a date. So that worked correctly. Now let's graph that real quick. So we pulled in X time and Y data too. So we want to do the Y first and then the X date. Is that correct? Let's see. Yes, here we go. So here's our graph for our date. You can see that at the bottom it says date. And if I double click on this axis, I have some options for how to display the date and time format. In the ticks and grids tab, I can do date format long. Let's try that. And here we can see that it changed to Sunday, December 15th, 2024, Monday, December 9th, 2024. So you can really edit how you want the format to look without changing the data at all. And that's some really nice formatting that's available to you in Igor. So the last thing I want to show is importing data that has a header and a footer. Sometimes your data is going to come in with a header and sometimes even a footer. And that's also going to be easy with Igor. All we have to do is we figure out what's the first row of our data and what's the last row of our data. I'm going to quickly make a notebook, a formatted notebook, just to make some notes here. The start of our data is line 20, and the end of our data is 12/5/83. So the end is 12/5/38, excuse me. That's really all we need to remember here. And we need to do a little math. So I'm going to just type out a command here, 20. Igor's counting for line numbers is 0 based, so 20 minus 1, and then plus 12/5/38. Since I'm in a notebook, I can just highlight that and I'll copy paste it. So we need 12/5/7 lines. I'm going to go to load waves, load waves. This one doesn't have wave names in it, so I'm going to uncheck that and go to tweaks. I'm going to go back to just the default date format, though it's not important in this time. Line containing column labels is none for this example, our first line containing data is going to be line 19, and the number of lines containing data is 12557. We're going to click OK. We're going to pick our file, which is this one here, and we're going to see how it did. So we have wave 0, that looks good. Wave 1, 2, 3, 4. It thinks there's a 5 because there were some extra spaces, but there isn't. So we're going to skip that column and load. Here we have our data. And it goes all the way to the bottom without any of the header or footer information. And so that's my demo.
Thanks a lot, Chris. That was very interesting. Even for somebody who's reasonably familiar with Igor, I've learned something new, and I'm pretty sure a lot of the audience got a couple tips and tricks along the way. And we can hear you. Yep.
Great. Okay. Well, thank you, Jan, and thank you to the Sutter team for inviting me here today. I'm very excited to talk about my work using dynamic clamp to explore how sodium channel gating regulates Purkinje neuron firing. And I wanted to start off with just a brief introduction to the cerebellum. And the cerebellum is classically involved in motor coordination, where it takes input from sensory information, integrates that information, and then sends the appropriate output. And this is just an illustration of a sagittal view of a mouse brain. And here we have the cerebellum kind of on top of the midbrain here. And if we take a look at one of these structures inside the cerebellum, this is called a cerebellar lobule. And we can zoom into this and we can see what's called the cerebellar cortex. And the cerebellar cortex involves a bunch of different neurons that regulate the output of the cerebellum. And I want you to pay particular attention to these green cells, and these are called Purkinje neurons. And Purkinje neurons are very important to the cerebellar cortex because they are the sole output of the cortex. And these neurons have the intrinsic capacity to fire spontaneously at very high frequencies, anywhere from 50 to 100 times a second. And this output is very important for cerebellar function, primarily because they are the sole output of the cerebellar cortex. And this high frequency firing is primarily mediated through sodium currents, which is facilitated through proteins in the membrane called voltage gated sodium channels. And here I have a sodium current, a modeled sodium current based off of a Purkinje neuron current. And I just wanted to go through all of the different current components that we can see here. So if we step our cell from a resting potential, such as -90, and we depolarize the membrane, the voltage-gated sodium channels will activate and open and allow for sodium conductance. They will very quickly inactivate. And this is what we call the transient sodium currents, or INAT. And so this is called fast inactivation or conventional inactivation. And that's what contributes to this transient sodium current. And if we keep this depolarization for a couple milliseconds, maybe 5 milliseconds in this case, and then we step back down to an intermediate voltage, such as -45 millivolts or -50 millivolts, some proportion of the channels that have undergone fast inactivation recover from fast inactivation and contribute to something called the resurgent sodium current, or INAR. And INAR is not as big as the transient current, but somehow these channels are able to recover from fast inactivation and open back up to allow current flow through the membrane. And then this resurgent current, as you can see, kind of decays over time. And it doesn't go back to baseline. And this is due to something called the persistent sodium current, or INAP. And INAP is contributed by channels that are not inactivating or are slowly inactivating and remain open and allow for sodium influx during this depolarization. And it's important to note that the resurgent current is thought to underlie this high frequency firing that we see in our Purkinje neurons. And I kind of want to shift a little bit to dynamic clamp that we can use through SutterPatch. And I can't really talk about dynamic clamp without talking about computational models, right? So this is our Markov state model of a voltage-gated sodium current. And each of these states represent the conformational changes that you would typically see in a voltage-gated sodium channel. So this is a closed state. Here is our open and conducting state. And then you have these transition rate constants in between each of these states that determine the math that goes between each of these states. And I wanted to focus in on two particular states, one of which is this fast inactivated state, which, as you remember from the previous slide, occurs after the transient current. So this is a very fast inactivation where it terminates that transient current and we get that really sharp termination of that current. And so while some of those channels can go from the open conformation into the fast inactivated state, other channels can go into what is called the slow inactivated state, or the IS in this case in this model. And if we depolarize the membrane enough, while some of those channels will go into fast inactivation, some of them will go into slow inactivation and remain open, but over time, those channels will not conventionally close, like the fast inactivation state, but will kind of collapse in on themselves, which terminates the conductance. So all of this to say is that we can use this Markov model to readily recapitulate all of the different current components that I mentioned previously. And we can do this through Sutter Patch and through dynamic clamp. So we can model this current on our computer, and then we can apply this current to real cells by connecting our software to an amplifier, which provides the current for dynamic clamp. And so if we're patched into a neuron, for example, a mouse cerebellar slice here, and we're patched into a Purkinje neuron, we're recording in voltage clamp, right? Or sorry, we're recording in current clamp, we're recording the voltage changes, the action potentials, the mathematical operations within Sutter Patch and within the model will determine the appropriate amount of dynamic clamp mediated current to be added afterwards. And that's what that looks like here. So on top in black, we have our action potentials that we're recording from these real neurons. And then in red, this is the dynamic clamp mediated current that's being produced by this nominal model, our baseline model. And after we add this current, this dynamic clamp current, what we see is a significant increase in firing frequency, which isn't all that surprising because we're adding a depolarizing current on top of cells that already have this current. So we're just increasing the current, which increases the firing frequency on top of our cells. But this allows us to really look into how firing frequency changes if we change properties of our model, which then changes properties of the current, right? So our first question was, what happens to Purkinje neuron firing if we want to scale the resurgent current in our model? And remember, we can simulate these currents by producing this nominal model with the transient, resurgent, and persistent components. But if we change and manipulate those rate constants in between the states, we can then create new models that change these current properties. So for example, we created two additional models, one of which decreased the resurgent current by about 63% comparatively to our baseline nominal model black trace here. We also created a model that increased the resurgent current by nearly 250%. So we have all three of these models. We can then add our models through dynamic clamp in Sutter Patch while we're patched onto real cells, and then assess firing frequency changes as we add the nominal, the increased resurgent current, and the decreased resurgent current models. And when we do that, we can then compare all of the firing frequencies that we see after we apply those models. So here we have our baseline nominal model firing frequency in our cells. After we added our resurgent current decreased model, that's this red trace here, what we found was a significant reduction in firing frequency, which isn't all that surprising, primarily because the literature tells us that the resurgent current kind of drives this spontaneous firing frequency. So a model that's added with a reduced amount of resurgent current, seeing a reduced amount of firing frequency is not that surprising. However, when we compared our increased resurgent current model with nearly 250% increased resurgent current compared to our baseline, we didn't see any significant differences, which really perplexed us. And so we really wanted to see how we can manipulate our models further to really break down what is exactly happening with this result here. So our next strategy was to develop models that vary not only in the proportion of the resurgent current, but also in the proportion of the persistent current. So in developing these models, we asked ourselves two questions. How does more resurgent current impact firing? But also, how does more persistent current impact firing? We can then apply those models to real neurons using dynamic clamp. And then we can assess how scaling the resurgent and persistent currents in those models affects the repetitive firing of those cells after we've added those models in through dynamic clamp. So we have our recordings of our cells that we have added our different models to it. And then we can compare those firing frequencies to the current properties of our simulated currents of each of those models. So we can test against the amount of resurgent current in those models, and then we can test the amount of persistent current in those models. And so here's a graph of the percent increase in firing frequency on the y-axis. So as we get higher, we have a greater increase in firing frequency in our cells where we applied the models. And on the x-axis, we have the amount of resurgent current within those models themselves. And what we see with this comparison, this is the resurgent current here on the x-axis. Even if we add a large amount of resurgent current, we're not really seeing a correlation between the amount of resurgent current added to the increase in firing frequency. And that's especially evident by our correlation coefficient R squared, which is quite low here. However, when we compared the persistent current in these models against the percent increase in firing frequency, we saw a strong positive correlation between the amount of persistent current and the firing frequency of these cells, suggesting that the more persistent current that is in these models, the greater the firing frequency. And you can see our correlation coefficient is much greater here. So this tells us two things: that the resurgent current does not necessarily scale firing, and that also the persistent current actually reliably scales firing frequencies. So that still leaves us with one more question to answer, right? And that's, what is the resurgent current's role exactly in Purkinje neurons? Because it's a really interesting current, right? And so we're going back to our Markov model just briefly, and we wanted to focus in on this slow inactivated state, this transition between the open and the slow inactivated state that is mediated through this rate constant A2S. And remember, we can create our simulated currents. This is our nominal model. And we wanted to decrease the transition rate constant that goes from open to slow inactivated state. So the model will spend more time in this open state. So we're decreasing A2S. And what happens when we do that is that we have an increased persistent current, but a decreased resurgent current. And then if we plot this over multiple models, as we decrease our A2S value, this transition rate constant going from the open to the slow inactivated state, we see this reciprocal relationship between the peak resurgent current on the x-axis here and on this z-axis here against persistent current. So we see this correlation between, this reciprocal relationship between the resurgent current and the persistent current. And if we add this new model where we've decreased this transition rate constant through dynamic clamp to our neurons, and we compare it against this baseline nominal current, we see a significant increase in firing frequency. So what does that tell us? That tells us that the persistent current is the one that reliably scales Purkinje neuron firing frequency. And it's the resurgent current that may act as a reservoir of sodium channels that are slowly inactivating, which contributes to the persistent current, and it is the persistent current that scales the Purkinje neuron firing rates. And with that, I would like to thank my advisor, Joey Ransdell, as well as our collaborators at Washington University, the Miami University Animal Facility, as well as the guys at Sutter Instrument, especially Telly, who has listened to a lot of my emails. Thank you so much.
Thanks a lot, Sam. That was a great talk showing dynamic clamp with the D-Patch amplifier system in SutterPatch software and how that's applied to a real-world question. And let me also highlight that this work has been published. The link to the Journal of Neuroscience paper was in the webinar invitation. And with that, let me switch to Telly, our last speaker. Telly, take it away.
Thank you very much, Jan. Today I'm going to talk about SutterPatch features that were not included in the original SutterPatch walkthrough videos. So let's get started. first, the small dashboard. The small dashboard was changed, so now it is fully customizable. You could have any number of icons that you wish to show or to hide. The acquisition control window is a central panel where paradigms or routines can be selected for execution. Paradigms can be started, stopped, paused, and resumed. Routines, which also include membrane test and free run, can be started and stopped. Please note that for acquisition purposes, this panel has the highest priority. And by that, I mean that stop acquisition and the stop at end of sweep settings here will take precedence over the ones that are in the scope window. User tags can be also selected and set here, as well as resetting the stopwatch timer. Another important feature that I like to talk about is found in the Sutterpatch pull-down menu, and that is Reset Acquisition. Reset Acquisition can be used to reset any ongoing or halted acquisition, restart the timer background tasks without exiting Igor and/or Sutterpatch. For those who are using multi-head stage D-patches, you can have a side-to-side control panel instead of switching between the tabs to go from one control to the next. We also added a show monitor that displays what's going on with the background task monitors. In this case, the voltage and the currents for each of the head stages, as well as all 8 of the input channels. The input channels can be used for monitoring external periphery that can be stored into metadata. How you will configure that is from the set preferences of the gear icon in the D-patch control panel, and you configure aux in monitors. Here you can transform a channel by giving it a label, a unit, and an equation to transform it. And if there's a metadata parameter that you want this assigned to, you could select it here as well. In this case, we're going to do bath temperature. Now, if you see in the monitors, as the background task is running, that input is getting scaled and then shown in the appropriate unit. 2 additional settings that I talk about from the D-patch control panel are the actual settings for control in the monitor updating. So typically you can set it for read signal inputs when they idle. So when there's no ongoing acquisition, every 250 milliseconds the monitors are being updated by a background task. We added recently a read signal inputs between sweeps, and this is for routine acquisition. Sometimes have a long start to start time where you want these inputs to be updated as well. So this allows you to do that, and then it will also update at the same 250 milliseconds. Another feature I'd like to talk about is the notebook window. The notebook was added originally as a text-only notebook, and we have since expanded it to cover both text and graphics. The nice thing about the notebook is it's stored along with the data. It's quite useful for storing all sorts of information. You can cut and paste into it from a variety of sources, including the Copy To button, which is available in many of our windows. And the Copy To button allows you to copy information from either our panels, our windows, our analysis. It's all over Sutterpatch as either a text or graph, and I can showcase this right now. So for example, from the control panel here, it writes down the information of what we currently had active. You could also do that as a graph as well. The notebook window also has this Copy To Export button. And in addition to the clipboard or to a layout, you could also store it as a text file, an RTF file, an HTML file, or you could print it directly. This makes the notebook a very powerful tool. I would like to talk about features that we've added to the oscilloscope window, and I like to bring up the membrane test window to showcase that. And what I usually like to do with membrane tests is I like holding down the shift key to do a reset of the control panel controls. So this gets everything into a known default state. Buttons over here, the so-called mode buttons, the bath, seal, and sell, actually play a very important role. They tell the software where to store the parameters. So in bath, the R pipette, R seal, and R series, R membrane, and C membrane are stored in a wave, which is then transferred to the metadata when routine acquisition is executed. To have the most up-to-date parameters, you want to run a membrane test before you run routine acquisition. But I just want to showcase a new feature here. It used to be a write to log. Now we converted that to a write to notebook. So we find that to be more useful. Our pipette, I have a computation. I put it in the notebook for storage. It's updated in the wave. Before I switch model cell to seal mode, I will change this button to seal. So this now locks in the previous setting. We go here, and now we will just perform an auto electrocompensation. And then we have a value here with a model cell. This is not really a great value because we don't actually have a resistor that's tied into that mode. So it's floating around and it could be any value. But just to showcase, we could put it in the notebook as well. Okay. Finally, before we switch, we go to cell mode. We switch our cell mode, and then we have our parameters here, our computer parameters for our series R membrane and C membrane. How close these values are to what the hardware computes is to run an actual cell compensation. So if you run an auto cell compensation, this is a multi-iterative algorithm that runs to compute the RS and CM. And then you compare the values here with what was done here. Now, as you notice, the values here are not valid because we removed the artifacts that it uses to compute them. So we could just disable cell compensation, and then we can get these values. And again, I'm going to write those to the notebook. Changes that we've made to the membrane test that are helpful, we now have the possibility to show the analysis fit trace. So you could see the fit trace used for these parameters. So you have an idea of where these computations are. And if you have enough data points, we should always be using a filter that's at least 10K or greater because you want a lot of data and you don't want to over filter or, flatten out these nice sharp edges for the curve fit. And we've also modified the line frequency noise reduction. We now have two options. We have the original FFT subtraction, which was showcased in the original videos, and we've also added a background subtraction. And the background subtraction, think of it as a P over 0. There's no pulses. What it does is it takes the same sweep length as our test pulse, but it has no test pulse actually associated with it. So it grabs and acquires that stretch of data before this actually runs, and it uses that data to subtract from this. Now, you can see here, there's actually some line frequency noise, and I'll make that even worse. I have an extension cord here that I'll just put right over the model cell to make it even worse. And you could see how the background subtraction works. So we'll do that. We'll add the signal. And we'll start that. And then you can see here the difference between the raw data, the actual signal that we're acquiring, and then the corrected with the background subtraction. It actually does a pretty good job. The background subtraction actually works better than the FFT subtraction for sweeps that are very short. Talk a little bit about the buttons that were added to the oscilloscope window. In addition to the copy to button that we talked about earlier, we've also made some changes to the buttons on the bottom here. We split the continuous auto scale button to two buttons, and the reason for that was to make it clear. It's a single one shot, so you do it one time. It does an auto scale on both the X and Y scaling. This enables continuous auto scale. Continuous auto scale will keep changing as you just saw the axis jump from sweep to sweep. It continuously auto scales a sweep. In membrane tests, you really don't want that because it's just jumpy, and the signal doesn't change so much. So we could disable that, and of course we have the buttons to work on the individual signals. You could auto scale the signal one time. In the y-axis, you could center it, and you could also reset the x-axis if you were playing around with any of the controls here. So the copy to button here has, again, as either text or graph. Here we could put the graph in the window, and then here in the membrane test settings window, where you put in there a text, will actually show the calculations that were being done in the membrane test. We could talk about the last button on the scope window. So first things first, let's stop this. Let's disable our fit trace, and let's also remove our excessive noise maker off our head stage. Start acquisition here. We'll go to our scanner button, and we will start with scan signal data. And scan signal data allows us to bring up the scanner. We could then go through and drag through and go to any particular point that we want, and we get an XY value as well as an index. Now this is very similar to the Igor cursor commands, except it's just a little easier to use and it's formatted in the right units. And again, our notebook window icon, slightly different here, but it comes to play. We can put information into the notebook as well. In addition to the scanner, we also have what we call the fitter. It looks very similar to our scanner. So first we start off with putting our starting point for, let's say we're going to go right over here and make that our set fit starting point. Then we're going to drag and add another point. Let's go somewhere around over there and set that. So now that's our window where we're actually going to be doing our fit. Then we can select our fit type that we like. Exponential sounds about right. And then we will do a fit to do it. We could play around with parameters. We could try different fit types and so forth. And as you go along, you can put the information into the notebook. Fit parameters go into the notebook. Or if you do copy, that same information will be added to the analysis editor window. Now, this fitter and scanner are available in many windows all across SutterPatch. Some of the new features that are available in the routine editor, and there's been quite a number of features that we've added along the past few years. One main feature is the ability to execute a routine without storing it. It's controlled by the button here, which just enables or disables the storing. And we made it on a routine basis and not a system-wide basis. That way it can't be left on or off. The idea here is you could duplicate routines. You can make some of them storing, some of them not. In the new version of SutterPatch that's coming up, 3.1, we actually now allow you to store this routine. So if you execute the routine, it's shown in the data navigator. As soon as the next acquisition is executed, that routine is replaced by the new one and it is now gone. But up to that point, you can still save it. Other changes, significant changes that we've made to Routine Editor are running average and cycle average. Now you have the ability to have a running average and only have results saved. We still have the cycle average and running average as virtual signals. That still follows the old style of acquiring all the data and storing all the data as you go along. These new features allow you sweeps as they're executing. You see that the real-time analysis is running for each of the sweeps. Then the final results are only the average results. And that's the case for both the average and for the cycle average. Run through a couple of examples of each shortly. Another change that we've made, again, based on a virtual signal, is the baseline subtraction. Though we've made a more simplified version where you just specify the region from the starting point to this particular time, it takes a mean of this value and then subtracts it from the raw data trace. Now this information is stored with the data trace, so down the line during the analysis, if you'd like to see the data in its natural baseline subtracted form, you could easily do that from the data navigator. And I'll show you how to do that. Other significant changes have been in the measurements. We added a number of new measurement types, some of the more important ones I'll go over. You now can use any one of the metadata parameters that are available as a measurement. Initially, that started as a way to bring in the timer information to be able to get, sweep timer, routine timer information. So we actually added those as individual analysis types, but then we also added a metadata which allows you to actually go and select any one of the metadata parameters that are available. If it's being used, you could select it and plot it as part of real-time analysis. Another significant measurement that we added was the ability to use user measurements. And what a user measurement is a function that actually goes out and looks at a specific IPF file. That IPF file is actually stored in Igor procedures. It automatically loads when you start up Igor Pro, and it follows specific format. So you could have any number of functions in there, but the actual function that actually ties back to the routine editor or to the real-time analysis in the routine editor or in the measurements for reanalysis is this function called user measurements. And these are the values that are passed to it. You have a source wave, which is the data wave that you're actually working with. You have a start time, end time, similar to what you have with other measurements. And now you have these three additional user parameters that could be anything you want. You write your own function to do whatever you like. This started out as a way to expand the measurements. A user wanted to do something specific. You wanted to compute a slope, which was based on first getting a time to peak measurement, and then 100 milliseconds past that, do a linear regression. So this is what that function is right here. And when you call the real-time measurements, if you specify the parameters and during the execution, it will automatically go to this IPF, execute this function, and return back a value that will be plotted and treated like any other user measurement. This is very flexible. It allows you to create basically any time of measurement that you want, as long as it fits within the boundaries of this function. Now, let's execute a couple of these routines to see how they actually behave. So first one, basically I took our IV routine, I modified it slightly, and I made it into a non-storing. So when you execute it, it executes same as any other routine, except you notice it says not stored in the background. Real-time measurements run, metadata is generated, real-time analysis is also computed and shown. In this case, we had it set for the notebook, so it's all run. And if you go look at the data navigator, you will see that there is an entry in there that's in red to dictate that this is a non-stored routine. It's here as a temporary placeholder. In the acquisition control window, we now have this additional icon. And if we click on it, it will automatically save this routine and treat it like it was a regular routine. Otherwise, if we go in and execute the next routine, that will automatically be removed and it will be replaced with the current routine that just executed. The previous routine that was not stored is not completely gone, and there's no way of getting it back at this point. Go through the cycle average of an IV. So basically this one is just going to collect 2 series and then average those 2 to give us back just the 1 series. So we'll execute that. So you can see here it's running. First series executed, the second series executed. The results here in real time showed both. The real-time measurements showed both running, but when you actually go back to the data navigator, you will see that you only have the 10 sweeps, which is the average results for both the current, the voltage signal, as well as the measurements. Another nicety that we added to the real-time measurements is you can now get information by clicking on the data points here, the X and Y values, and it also points back at what sweep this data is associated with, and it automatically loads a sweep. Same thing, if you go here and you select a sweep, it will automatically go and show you the result in the real-time analysis. Again, our favorite button, the Copy To button, is available for copying results to the notebook, to the clipboard, or to the layout. So again, as text or as graph, adding, building up to our notebook as we needed. Finally, I'd like to talk about the data navigator, and more importantly, the data tree filter. This is a way to basically data mine or to filter out your data set, your whole experiment file based on metadata parameters. So first things first is you build a tree filter. So you specify what parameters you're looking for in the data, and those are a variety of different metadata parameters. You have a frequently used list. You then could go through all the individual ones. So for example, you want a particular data acquisition setting that you're looking for, like recording mode, or if there's a certain value for cell compensation, you can specify that. You copy it over to the data filter. You'd say what signals you actually want to look at to compare, and you set that, and then you have that and you copy it to the pool and you activate it. Once the filter is enabled, it will sort the data tree based on those requirements. And in this case, none of the data actually met the requirements of our tree filter, so we're seeing a blank list. Now keep in mind that this is strictly for viewing and for sorting, so the original data experiment file is still saved and still intact with all of the data set in it. So let's disable the tree. Let's open up a routine for analysis, and I'd like to now talk a little bit about how measurements play a role in this new reanalysis as well. So from the measurements button, we have edit measurements, and measurements are stored if they exist in a routine. They are stored as part of the routine copy, and that information is available when you're doing reanalysis. If you want to execute measurements that were from another routine or from another data copy, you can now load them. So this is a new feature of where to get measurement information. You could get it from an existing routine, or you can get it now from a file. So you could actually store and get measurements that you store in a variety of measurement files. So we create a measurement file, and now we have this file available and to be used. And the nice thing about having it in a file, that means that when we load another experiment and we want to run the same measurements, we could easily get those measurements from that file by loading it from here. We could also load measurements from a routine that's already in the pool or from a data copy. And the data copy I'm referring to is the actual routine copy that's stored whenever routine is executed as part of the data acquisition. The final thing that I'd like to show you is how baseline subtraction is modified in the Data Navigator. We store that information, so in the Data Navigator, you have the ability to basically un-baseline subtract the signal if needed. And that's what I'm showing here. You could revert back to the original data set without the subtraction. You could also apply a background subtraction, a baseline subtraction here as well. And I think that was all the time that I actually had for this video. And I mean, there's a lot more features that I would like to go into, but that's for the next upcoming video in this series.
Thanks a lot, Telly. Since you mentioned SUDR Patch 3.1, I would like to emphasize this has not been released yet. It's in regression testing.
Correct.
And we hope to be able to release it pretty soon. Some of the features you talked about were not available in SUDR Patch 3 yet. We have a whole number of questions from the audience. And actually, let's start with one that is related to SUDR Patch 3. The question is about pClamp data, and it's rather long. I'm not going to read the whole question. In essence, the question is, how can you make pClamp data available to analysis in native Igor or in SUDR Patch?
Okay, in SUDR Patch, we have in the Data Navigator, you could actually see it on my last screenshot here. You can see that there is an import button. And this import button, if you click on it, allows you to select different files to basically import into your current experiment file. And we import both ABF 1. I believe it's 1.6 and above, and 2.0 to 2.07 ABF files. So once they're in the SUDR Patch world, then they are available for analysis, real-time measurements, analysis, and so forth. Everything that's available in SUDR Patch. That translated ABF data is, when it comes to SUDR Patch, is tweaked and altered so it matches what is required in SUDR Patch, which doesn't mean that it's exactly correct for Igor functionality, because it uses our multidimensional waves, it uses our structures for the information regarding stimulus and so forth. I did promise everyone at Wavemetrics that I was going to make a set of procedures available to the general public that can be used to import ABF and HECA files directly into Igor waves and not the SUDR Patch world. And that's going to happen sometime in 2025.
Okay. And we should also highlight that SUDR Patch 3 is free to download, and you can use it to import pClamp data as long as you have an Igor license. That's the only requirement. SUDR Patch itself has no restriction anymore. So even if somebody is not a SUDR amplifier system customer, they can use SUDR Patch to analyze their data. And actually, we have a number of customers who do that, record with either Axon or HECA hard and software, and then do the analysis within SUDR Patch.
So with one thing I forgot to mention earlier was HECA Next data files are only supported with version 3.1. They were not supported with version 3, while the ABF files were.
Okay, the next question also for you, Telly. When using SUDR Patch and saving your analysis, it copies units from the table. How to copy and paste only the numbers into Excel, etc.?
Yeah, so two things. One is what is shown in the analysis editor window is a text representation of the data. That's why we show units. That's why it's in certain columns. It has dimension labels all shown in the table. In set preferences, you can actually define what this actual data looks like. So the data itself is stored in double precision 64-bit floating point numbers. You can, when you do an export, and by export I mean copy to clipboard or export to an Igor wave, a single dimensional wave, or so forth. There's a preference in Sutterpatch set preferences that allows you to define if you're using exponential notation, general notation, or scientific. And for Excel, you want to use a scientific because it doesn't know anything about P's and F's and micros and so forth. One of the export types that we have in Sutterpatch for tables in particular is a way to copy, instead of exporting it out as files, we can create either single dimensional, multi-dimensional Igor waves within the Igor environment. So what we call that as a wave copy, you specify a folder, which is a virtual folder within the Igor environment, and then you can put that data there in the format that Igor needs. And that whole process is shown in my last webinar recording, importing and exporting data.
Okay, the next question is for Sam. Nice illustration of using a complicated Markov model in dynamic clamp. I totally agree with that. Technical question. What was the sampling or update interval in the dynamic clamp implementation?
I think we use the fastest possible update interval. Telly can speak to the exact numerical value, but I believe it is around 200 kilohertz or something like that. So it's the fastest that we were able to apply it.
Okay.
Yeah, so in Sutterpatch, the dynamic clamp, you can, depending on how many states your model has, you can go up to as fast as a 500 kilohertz update rate. But again, it all depends on how complex the model is.
Right. And then the question goes on, but it's actually a separate question, biological question. In the combined data, there was no statistical effect on firing frequency of increasing resurgent current, but in some individual cells, it did have a big effect. Do you know what the key differences are between the cells where increasing resurgent current did increase firing frequency and those where it either had no effect or actually slowed the firing?
Yeah, that's actually a really good question and something we absolutely noticed during our data. And this kind of differential effect of the dynamic clamp, it may reflect the heterogeneity of the complement of channels that are present in the cell. We didn't necessarily look at analyzing cell-to-cell differences, but I would say that it would probably be the heterogeneity of the channels. Yeah.
And related to that, a question I have. I noticed in the first figure you showed that 4 of the cells did increase their firing frequency a lot less than the majority of the cells. Did you have a chance to check whether that's a different population, or do you have a hypothesis to that?
No, I think pretty much the same answer, right? So these cells are incredibly diverse, even within the same population. So that may account for the differential effect. But we didn't analyze those cell-to-cell interactions. No.
Okay. And then a question for Chris. What is the difference between importing general text and delimited text?
Yeah, so that's a great question. So general text is going to be data that has no missing values, no nans or empty cells. If you have kind of trickier data, then you're going to want to use delimited data. Delimited data can load numeric text, date time data, and also handle missing values, nans and infinities and negative infinities and all that sort of thing. So that's the basic answer. General text is going to be, it needs to be very well formatted and formed.
Okay, thank you. Then we have another question for Telly. Some other amplifiers have allowed rapid switching from voltage clamp to current clamp in the middle of the sweep. This can be useful, for example, applying voltage clamp at a certain point during action potential firing, for example, during a cardiac action potential, or evoking an action potential after well-controlled pre-pulse voltages. How fast can the switching be from voltage clamp to current clamp, and can it be pre-programmed to happen during a sweep?
Yes, but only for the D-patch. So in the D-patch, we have a couple of features which we call in-sweep actions. And basically, in an in-sweep action, you could define an event either by specifying a duration, a time point when this should occur, or by looking at a threshold. So you could define an input signal, you could define a threshold, and you could say, okay, once we reach this threshold, I want you to do this action. So the actions that we support currently are switching from one recording mode into the next. You can change a holding value. You can set digital lines that way, and also auxiliary outputs. In-sweep action can fire within a single sweep, can fire twice. Basically, the time point for the first one, and then you could revert back after a set period of time.
Okay, and the good news is that the attendee who asked this question happens to own a D-patch, actually more than one. Interestingly, another attendee had a very similar question early on after receiving their D-patch, so that seems to be related. The electrophysiology world is small, you know people after a while. Okay.
Jan, just one quick note on the previous question. I just realized that, yes, the IPA can also do it, but not in a timed fashion. So the IPA control panel will allow you to switch between voltage clamp and current clamp and vice versa, but only manually through the control panel, not in a time sequence, unless you're doing something within a paradigm.
Okay, thank you. Let's have another quick question for Sam. Why did you use all current components and not just the resurgent sodium current?
Yeah, we were primarily interested in the interactions between each of the current components. So we wanted to see if we adjusted one of the current components, how could that adjust firing? And, adding simply just the resurgent current or simply just adding the persistent current, because they're depolarizing potentials, that would most likely just increase or decrease firing frequency. So we wanted to kind of look at the whole complement of current components to see how they affect firing.
Thank you. Another question for Chris. Can you use a liberal name for column header in the import data file? And a liberal name, if I remember correctly, it would be defined as something that has special characters, including a space in it, correct?
Yeah, that's right. So I showed a liberal name in the data that I imported from the example PXP file. You saw that it had a space in it. So when I needed to type the names on the command line, I had to quote them with a single quote. So if you have a liberal name, a name that has, special characters or spaces in it in your column names for the data that you're going to import through an import file, what Igor is going to do is going to replace any of those special characters or spaces with an underscore. So it imports it fine, but you'll find that the name will be deliberalized. It'll turn into a standard name with underscores.
But then Igor can handle liberal wave names if you...
It can handle liberal wave names. The reason why it changes them is because you want to be really careful if you have a CSV file and your delimiter is one of the characters that's in your liberal name. So if you had like a file where you're using spaces as a delimiter and you have a space for your column header name, that's going to get a little hairy. So we'd probably advise against that. So that's one of the reasons why we just put in underscores just during import. If you wanted to keep those liberal names, you would want to use the /b flag on the load wave command, and you'd want to probably put together a load wave command by hand for something that very specific. So if you looked up load wave in the Igor help, the /b command has its own section that's several pages long. It's very powerful flag to the load wave command, and you can pretty much handle any sort of input that you want. You can handle different columns. If you, for example, had a import file that had multiple date columns, for example, and they were each a different format, you'd be able to handle that with the /b flag.
Okay. Yeah, it's interesting that you bring up the overlap between delimiter and special character in the actual data. One software platform that is very common for PatchClamp does exactly that when it puts out the results in the equivalent of a notebook. It uses multiple space characters as the delimiter, but then there can also be spaces in the actual results, and that makes it very hard to
Yeah,
do
that's tricky.
efficient analysis of that in any other platform. I think we are through most questions. One more here for Telly. Is there a way to have aux-in monitors for the IPA amplifier system?
Actually, yes. The original implementation of the so-called aux monitors, it was built in as part of the real-time analysis. So real-time measurements support equations, and what we have in equations is what we call special identifiers. And the special identifiers allow you to select amplifier-specific parameters. And in the case of the IPA and the D-patch, the aux-in channels are part of the amplifier special identifiers. So basically, you would have the same thing. You would select this parameter, and then you would transform it with an equation, and then it would show up as part of real-time measurements.
Okay, thank you. Let's have one last question and then the rest by email. That is for Sam. What is the INAR doing in other cell types?
Sure. Thank you for that question. The resurgent current was originally discovered in Purkinje neurons, which is why we are primarily looking at Purkinje neurons. But other cell types with the resurgent currents in central neurons don't necessarily fire as quickly as Purkinje neurons. So the resurgent current may be doing something completely different, and the resurgent current may be cell-specific in its behavior across cell types. But our study only looked at Purkinje neurons.
Okay, thanks a lot. And with that, let me thank the speakers today. Let me particularly also thank the audience for dialing in. And we had quite a few people, considering that we've not drummed up a whole lot of attention for this webinar. As I said, all questions that were not addressed during the Q&A session we'll get to by email. If there's any follow-up questions, then feel free to shoot us an email. You know most of our email addresses. And again, thank you very much for being here. And that concludes this webinar. Have a great day. Bye-bye.